Hey everyone, welcome back, and today let's solve LeetCode problem 2598 titled Smallest Missing Non-Negative Integer After Operations. So we're given a zero-index integer array nums and an integer value, and in one operation we can add or subtract value from any element of nums. For example, if the input array nums is equal to 1, 2, 3, and value is equal to 2, we can choose to subtract value from nums at index 0 and make nums negative 1, 2, 3. In other words, all we're doing is we're subtracting 2 from this 1 value, and that's basically just the 0th index of our input. And so 1 minus 2 is negative 1, and so the resulting array after that specific operation would become negative 1, 2, 3. Now the MEX, or the minimum excluded of an array, is the smallest missing non-negative integer in it. So for example, the MEX of negative 1, 2, 3, the resulting array that we got after that one operation in the other example above would be 0. The reason why is because 0 is the largest, or rather 0 is the smallest non-negative integer that isn't in this input array. Right? Notice how non-negative integers have to start from 0 and they go up to 0, 1, 2, 3, and so on and so forth. And 0 itself isn't in this input array. And so even though 1 also isn't, since 0 is smaller, that is the smallest possible non-negative integer that we can get that's not in this input array. And so 0 is, in other words, the MEX of this input. Another example would be 0 or 1, 0, 3 rather. 0 is in it, that's where we start. 1 is also in it, that's great, but 2 isn't. And so since 2 is the first non-negative integer starting from 0 that isn't in this input array, 2 is also the MEX, or the smallest non-negative integer that's missing from this array. And so the MEX of this array, 1, 0, 3, would be 2. Now our task is to return the maximum MEX of nums after applying the mentioned operation any number of times, right? We don't particularly have a restriction on how many times we can apply this operation to whichever elements we really want to. Right? Which really just gives us the goal and main observation of, great, well, we want to just basically get all the values subtracted or added as close to 0 as possible. Or in other words, check off all the boxes or all the smallest negative integers as much as possible, right? Because best case scenario, if per se the length of our input array is 3, our MEX would be 3. Right? In other words, the best case scenario would be the length of our input array nums, right? Because we'd have 0 checked off, 1 checked off, and 2 checked off, meaning 3 would be the MEX of our input array if we had an input array of length 3 in the best case. Meaning we have all the smallest non-negative integers up until the actual number of elements we have. That's kind of like our best case scenario, and that's really what we're trying to fulfill to maximize our MEX, right? So if I had something like 0, or 0, 1, 2, 3, obviously this is best case because the MEX of this is 4. If I had something like 0, 1, 6, 3, the MEX of this would be 2, right? Of course, 4 is the maximum value we can get because that is the length of this input array, right? That's kind of a good observation to really think of in the back of your head. Right, and so we're trying to get every value to check off every other possible smallest non-negative integer to maximize that value, MEX. So in example 1, we have our input array nums to be 1, negative 10, 7, 13, 6, and 8, and our value to be 5. In other words, that just means that we can subtract or add 5 to any element any number of times we want, and that's basically just one operation. And keep in mind, we have unlimited operations. We can apply the operation to our input any number of times. Now, in this case, the smallest non-negative integer that we can actually get, or in other words, the MEX of this input array nums, after infinite operations, or after all the operations that we really need to maximize MEX would be 4. And the way we do that is we'd effectively just add value to nums at index 1 twice. Negative 10 would go to 0 because 5 plus negative 10 is 0. Then we'd subtract 5 from 7 to get 2. Then we'd subtract the value from 13 twice to make it then 3, right? And so we'd have 0, 1, and 2, but we couldn't actually form 4 or 5 or anything like that from the other elements. And so because of that, 4 would be kind of like our bottleneck or our MEX for that input array, right? Because we cannot form 4 with any of the other elements applying or subtracting or adding a value of 5 any number of times. In example 2, I'm just going to quickly gloss over this. The output would be 2 because we could form 0, we could form 1, but that is it. We cannot form 2, and so that's where we have to kind of stop our iteration. That's another very important observation to make. The moment we can't actually make something in that sequential order from 0 to whatever, we have to immediately stop and return that value. Why? Because if we can't form 2 from any element, we know that's going to be our MEX. We can form 0, we can form 1, but if we can't form 2, even if we can form 3, since 2 is smaller than 3, 2 is like our bottleneck, and so that's going to be the MEX of the input array nums. right? So for the constraints here, we see that the length of our input array nums and our value are going to be both between 1 and 10 to the 5th power, and any value itself in the input array nums is going to be between negative 10 to the 9th power and positive 10 to the 9th power, which leads us to the kind of structure of our solution based off of the observations that we really made as we went through the example. So how are we really going to solve this problem? Just a really kind of glossed over solution. Effectively, we're going to use a frequency map. In other words, that's just a dictionary, or in this problem's case, a default dictionary in Python. Effectively, the whole point of that dictionary is to count how many numbers in nums have a remainder of r equal to num modded by value, right? And that r is going to be in the range of 0 to value minus 1. We're also going to keep track of an integer MEX that we'll try to build from 0 upward, like we saw in the examples. We're going to start from 0 and keep checking off boxes as we sequentially go up in order by 1 each time. And the moment we form a non-negative integer that we cannot form, that becomes our MEX, and that we immediately return that value. So, effectively, in short, how are we really doing this? What is the kind of structure of our algorithm? Effectively, we're first counting the remainders, or pre-processing part, if you will, using our frequency map, right? For every I equals 0, I equals 1, I equals 2, and so on and so forth, we're checking the remainder to be the value r, which is just I modded by the value. And if the count at that index r, again, count is simply our dictionary, at that index r, if it's greater than 0, we can assign one number to represent that I, and then decrement count at r and continue on that operation. Now, if count at r ever equals 0, we cannot actually build I, and so I would be kind of like our bottlenecks or maximum achievable smallest integer. And so that would be our maximum achievable MEX. And again, tying back to another very important observation to really make, the maximum possible MEX cannot exceed n, which is the length of our input array nums, plus maybe a small constant, because to actually construct k distinct non-negative integers, we do actually need at least k elements. And really practically, and really for this problem's constraints, we really need to try up until n plus 1, or iterate until the count actually runs out. And so really, in practice, this is going to be a pretty linear runtime complexity. It's going to use big O of value or big O of n extra space for counts, right? But I'm not going to get too deep into that just yet. Let's go ahead and get into the actual solution and the actual coding part of this solution. So the very first thing that we're going to do, like we talked about in the problem statement, like we talked about in the examples and the algorithm overview, effectively we're going to initialize our count. This is just our pre-processing or our pre-processing default dictionary, or hash map, if you will, in Python. It's going to be initialized to a default dict of type int. Now, the whole point of default dictionaries is that we're simply passing in this data type here, and so every key that we're checking to be in this kind of hash map, even if it doesn't actually exist in the data structure, it's going to have a default key of 0, right? And the reason why it's 0 is because that's the default key value pair of any integer type, and we're passing in or inputting an input integer data type, and so it's going to have an assigned value of 0. Right? Effectively, the whole point of this default frequency dictionary is to map each remainder r to how many numbers in nums actually have that remainder. And default that any int is going to give, again, 0 for any of the missing keys automatically, even if they aren't in our dictionary at that time. Once we do that, now let's actually begin iterating over our input and building up our default dictionary for the specific remainders as we actually try to construct numbers starting from 0 and going, or kind of building our way out, right? So for every, let's just say x as our iterator in the input array nums, our remainder value is going to be the current value x modded by our value, whatever that value is here. That's our input, by the way. And we're going to then set count at r and increment that remainder by 1, because of course we're seeing that remainder one more time in this specific iteration. And so its frequency is going to be incremented by 1, right? We're effectively, this is basically just going to be the next integer that we actually attempt to construct, right? So we try to construct 0, then we try to construct 1, and so on and so forth. Right? And that's basically really it for our building part, or our pre-processing part, to build our frequency hash map. And now we can actually get into the main kind of validation and MEX part calculation of this solution. So, exiting this for loop here, let's now initialize our I value to be 0. Effectively, we're just going to run a while loop forever until we actually find some I that we cannot construct. That's going to be our bottleneck, or our maximum MEX value that we ultimately end up returning, right? And once we actually find that maximum MEX value, we're going to break when that actually happens from that kind of forever while loop, right? And so for readability, in Python, a really nice way to do that is simply just use the while true loop and just break explicitly once we actually reach that desired maximum MEX value, when we can no longer form it from any values or inputs in our input array nums, right? So while true, like we just talked about like seconds ago, right? Effectively, we're just going to consider the residue class where we have to actually need the current. I equals R equals I modded by value, right? So effectively, while true, while we're still trying to find different maximum MEX values, right, we're going to get the R, and that's going to be I modded by our value, right? Which really means if count at R is positive, that means we have at least one number whose remainder does equal R, and so we can transform that number to equal I by either adding or subtracting value the right number of times from that element, of course, right? And so we have to then decrement count at R to mark that we used one such number, and then actually decrease its frequency by 1, and increment I to try the next integer, right? So the way we do that is if count at R is greater than 0, meaning it has at least a frequency that's positive, we're going to then use it, so decrement its frequency by 1, so when it's equals 1, and then increment our I value by 1, and then continue on to the next iteration here. Effectively, if count at R is 0, we cannot actually form I, and so I would be the maximum MEX achievable, and so we then return it if that is the case. And that would then end the algorithm, right? And the way we'd actually handle that is simply just, you guessed it, to return I. So if that's the case, we'd simply just return I, right? That's basically just the full kind of main kind of thought process, right? Because if we can't form I, meaning it's 0, right? If count at R more specifically is 0, that is the maximum MEX achievable. We have to immediately return that. And that basically just ends our kind of solution. We immediately return, and so we automatically break out of this while loop. And that actually is it for the solution. So unless I made any syntax error, this should be accepted. This should be spelled correctly, or rather submitted correctly. All right, let's see. Okay, this should be count, not count, CNR. Sorry about that. Let's go ahead and resubmit this and see if it works. And as you can see, this really is just about as efficient as you can get it to be. So again, on a high level, how are we really solving this problem? Effectively, just to gloss over the summary, we're just first counting how many numbers actually fall into each remainder class using the modulo value, and then starting from 0, we're just greedily trying to build consecutive non-negative integers, starting from 0 and building our way up, so 0, 1, 2, and so on and so forth. And to actually construct integer I, we need a number whose remainder is I modded by value. And if such a number does exist in our input array nums that we built over from our frequency map, we then use it by decrementing its count and then moving on to the next kind of integer, or I plus 1, until we can't do that. And if we can't do that, meaning if we can't actually build it at that iteration, we then stop and we return I, because that I would be the maximum MEX that we cannot reach. And so it's the maximum possible value that we can really form after all the operations. That's the first value that we can't form, and so that's what we return. And again, tying back to that main observation, because each element can only realize values in its residue class, we're simply just consuming those residue resources one by one to actually produce our consecutive integers until we can't actually form another value I, and that would be our MEX value that we can't form, and that would be what we return to exit out of our while loop and break out of the algorithm, right? Which brings us to the final part of this solution, and that is simply just the complexities, right? So for the runtime complexity of this solution, it really is just big O of n plus MEX, which really in worst case is, again, like we talked about, just big O of n or linear. And the reason why is because in reality, this really is just a one-pass solution technically, right? We're just really only using one pass to build the counts big O of n. And although we are actually then incrementing I at most once per successful construction, I cannot exceed n plus something very small, or effectively just n, right? Because each constructed integer would consume exactly one original element. And so the second phase would also technically be big O of n worst case, and usually it's much smaller than that. And so really, fully simplified, is just big O of n or linear, right? Because constants and coefficients don't matter in memory and runtime complexities. Which brings us to the memory and space complexity, and that's going to be the big O of minimum of n and value, which is essentially just big O of value in the worst case. Why? Because we're really storing the counts for the remainder classes from 0 up until value minus 1. And if the value is actually larger than n, that is, we'd only still need a storing at most n distinct keys, and so it'd be big O of the minimum of n and value for our memory or space complexity, right? So in short, linear time and linear extra space, right? So if you guys enjoyed the solution and learned something new, please consider liking this video and subscribing to my channel, and without further ado, I will see you guys in the next video. Bye-bye.